using a second order Taylor's polynomial to approximate the function f. So this one is the Taylor's polynomial, and then we use this to approximate the function log x squared plus y squared plus 1. And then we also want to get an approximation or some estimation for the error term. Eventually, I will show that for x, y, which are bounded above by 0.1, then the error term here is bounded above by 0.000x3, something like that. And so of course, the bound here may not be the best, but at least I can obtain a certain bound by using the remainder term in the Taylor's theorem. So here I just want to demonstrate how we can apply that result to find out such an estimation. And then you may say that this error term is already very good. So that's why this polynomial is a very good approximation to the original function here. Okay, so of course, when you use Taylor's theorem, you first need to fix the reference point. Very often, the point is given in the question. So you don't really need to worry which point to choose. Or sometimes it depends on the setting of the question. Maybe I only consider those points x, y, satisfying the absolute value are bounded above by 0.1. So the set of all points satisfying this condition is a square. So the length is actually a 2 times 0.1, and a center is the origin. So it is very natural to use the center of the square to set it as the reference point, because it keeps some kind of symmetry of the expressions. So that's why even if you are not given this information, I think it's natural to choose the origin to be the center of this square to be the reference point here. Okay, and then if you have taken a look at the proof here, actually it is very lengthy. I actually write down many pages for the whole proof. But at least you need to understand the whole idea. Maybe in some simpler question, it is possible that I may give you some of the expressions for the derivatives, so you don't need to do so much computations. But you still need to understand the whole process in order to see what to do when you want to find such an approximation of the function. Okay, but if you're not given any information, you have to do all the things on your own. That means first of all, you have to find out all those first order, second order partial derivatives of the function. Now here I will miss all the computational details. So if you wish, you can try to verify all these things. So you may expect this already takes you a lot of time when you compute all these derivatives of the function here. Okay, so assuming that we already know this, or they are given in the question, then you can directly work out the second order Taylor's polynomial. So the main term is this degree 2 term. Again, it contains the degree 0, degree 1, and degree 2 terms. You basically substitute x equals y equals 0 in all those derivatives. So you will get some constant matrices like that. Then you can expand the whole thing and then get a very simple degree 2 polynomial, x squared plus y squared. Okay, so if you are just asked to find an approximation, normally it's good enough to find the main term. But of course, in some questions, you are also asked to find an estimation of the error term. So that's what we are going to see how to do. Then we have to apply that proposition for Taylor's theorem to work out an expression for the remainder term. So recall that for a degree 2 approximation, the error term here involves degree 3 terms. So it involves the x cubed, x squared, y, xy squared, and then y cubed. And then all the coefficients involve the third order partial derivatives, acting on a certain points lying between 0, 0 and the point xy. Now recall that the point xi lies on the segment joining the 2 points. That's the meaning of the line between some points. And of course, in general, there should be x terms here in the third order expression. But here you can see that I also combine some terms together. So there are 3 terms which are the same as fxxy, which are fxyx and also fyxx. Because we already know that the function is smooth, so it is of class C3. So all those third order partial derivatives are continuous. So you can again apply that theorem to show that all these permutation of the indexes actually give you the same partial derivative. So the same for the term x, y, y here. You actually have 3 terms in total. Anyway, so that's the theoretical expression for the remainder term. If you want to get an estimation, which means a certain upper bound for the absolute value of this error term, then you have to estimate each term one by one. Now, very often you can consider these 4 terms separately. Now, you don't really need to get a very tight bound or a bound so that the maximum value can be attained. There is no need to do so. Usually it suffices to get a convenient way to find the upper bound. So the most convenient way is to consider each term one by one, or mathematically it means to apply the triangle inequality. Okay, but in any case, you still need some estimation about the third order partial derivatives. So here I actually write down all the computations again. So once again, that means you actually need to further compute all these third order partial derivatives. Okay, so let's see how we can estimate each term one by one. So recall that's the information of the factor xi. So that is entry xi1, xi2 also satisfy this inequality. This is because x and y are bounded above by 0.1. So if these points are still lies between 0 and xy, that means, of course, they still satisfy the same constraint. Or another way to see is that recall that the set containing all those points xy is actually a square. So the point 0, 0 is somewhere here, xy is somewhere here, and then we say that xi is something lying on this segment. So of course, this point xi still lies on the square. So in other words, its entries also satisfy the same inequality. Okay, we can already use this information to get some approximation to the third order partial derivatives.